Hey guys, our last chapter, chapter 9, probability. Okay, so first we have some definitions. Experiment, an activity whose results can be observed and recorded. Outcome, each of the possible results of an experiment. Sample space, a set of all possible outcomes for an experiment. Event, any subset of a sample space. Okay, so what that means, let's say, so our experiment is the actual activity. So let's say we want our experiment to be rolling a single six-sided die, right? That would be our experiment. The outcome would be, if we roll the die, what it actually lands on. The sample space is all the possible outcomes. So for this experiment, the sample space would be the numbers 1 through 6, anything that's possible for us to have landed on. And an event is a subset of the sample space. For example, we might call our event O if we were talking about rolling an odd number. Then our event would be 1, 3, 5. Or we could talk about the event E, rolling an even number. By the way, we typically shorthand our probabilities with a capital letter. So our event would be 2, 4, 6. We could have an event saying the multiples of 3, right, which would be 3 and 6, or the event a number less than 4, on and on and on. Okay, so the experiment would be the actual rolling the die. Outcome, what you actually roll when you do the experiment. Sample space, anything that's possible, and events, what you're interested in seeing if you roll. Okay, notice I did retry that little broom, which I thought was it earlier, and I couldn't make it erase everything at once, but I guess it wasn't actually clicking. So I did find that one, which is handy. I'm sure y'all will appreciate it too. Okay, suppose an experiment consists of drawing one slip of paper from a jar containing 12 slips of paper, each with a different month of the year written on it. Find each of the following. Okay, so it says find the sample space. Well, remember the sample space is everything that's possible. And so it would be every month of the year, January, February, March. That's what's in the jar on every slip of paper. And what would event A be if you wanted it to be a month beginning with J? Okay, so then this would be January, June, or July. Okay, or you could have your event being months that end in BER. And then it would be September, October, November, December, etc. Okay, I don't know if y'all can hear that or not. My phone rang. My husband answered it in the background, so it's distracting me. Okay, let's see. All right, we've got two different kinds of experiments. We've got empirical and theoretical. Okay, empirical experiments are also called experimental. Okay, and they're determined by observing outcomes of experiments. For example, say we wanted to know the probability that this particular basketball player is going to make his next free throw. Well, we don't really know what that would be. It's not a 50-50 chance, you make it or you don't. I mean, those are technically your outcomes, but we would look at the last 1,000 times he has shot a free throw to see how many out of that 1,000 that he's made, to make a prediction on how likely he is to make this next one. Or, of course, this is what they do in the medical field when they do experiments on mice and find, well, what's the probability this drug is going to kill us? Experimental probabilities versus theoretical probabilities. Now, their definition says the outcome under ideal conditions, but those are the things where we know all of the outcomes and this is going to come into play equally likely. Like that single six-sided die we were just talking about rolling. That's a theoretical probability because I know exactly what the outcomes are and that they're all equally likely. Flipping a coin. You're only going to get a heads or a tails, and assuming the die and the coin are not weighted, right, they're equally likely to happen. Drawing a card. There's 52 cards in a deck, so you know exactly what every possible outcome is. It's also important when we're doing probabilities that they're equally likely. And that's when one outcome is as likely as another to happen. Okay, that's why I was saying that throwing the free throw, yeah, there's two outcomes, but they're not equally likely, right? Depending on how good you are at basketball. But rolling a die, drawing a card, we know how many outcomes they are, and they're all equally likely. You're just as likely to reach in and draw the ace of spades as you are the two of clubs. We call it a uniform sample space when each possible outcome of the sample space is equally likely. Okay, so speaking of those theoretical probabilities, we have something called the law of large numbers, or Bernoulli's theorem, right? Also called Bernoulli's law of large numbers. You might have noticed, I'm not sure if the Bernoulli brothers are on the list of possible mathematicians for you to do your papers on, but there were brothers, that lived hundreds of years ago, John and Jacob. I think this is actually one of Jacob's theorems. They were famous mathematicians of their time. And also, I'll warn you, a lot of these slides, use that crazy English to explain their ideas. So hopefully watching these videos, I can break that down a little bit. So here's how they're stating Bernoulli's law of large numbers. As the number of trials of an experiment increases, the experimental or empirical probability of a particular event approaches a fixed number, the theoretical probability of that event. Okay, what does that mean? That means we know that the theoretical probability of flipping a coin, for example, right, and getting a heads is 1/2. There's two choices, right, a heads or a tails. One of those is a heads, so the probability is 1 out of 2, right, 1/2, 50% chance. But that does not mean if you flip 10 coins, you're going to get 5 heads and 5 tails. As a matter of fact, that would be really, really unusual. Right, if your experiment is flipping 10 coins and counting the number of heads and the number of tails you get, you probably would get 7 or 8 heads maybe, or 7 or 8 tails. But what this is saying is the more and more times you flip that coin, if you flip that coin instead of 10 times, 100 times, you'll get closer and closer to that 1/2 probability. If you flip it 100 times, if you flipped it 10 coins, let's say you could get 7 or 8 heads. If you flip it 100 times, theoretically you should get 50 heads and 50 tails. So you might, get 42 heads or 44 heads. If you flip it 1,000 times, theoretically you should get 500 heads, 500 tails. If you flip it 10,000 times, of course, 5,000 heads, 5,000 tails. And the more and more times you flip that coin, as your experiment size increases, you'll get closer and closer to that theoretical number. So that's what this law of large numbers is telling us. All right, we already talked about a little bit how to calculate probabilities. So this says, for an experiment with non-empty finite sample space S with equally likely outcomes, the probability of an event A is, okay, and here's our notation for doing probabilities, right? We'll write it like this. Here's our event. And all we do, like I just mentioned about the flipping the heads, flipping the coin and getting heads. So we count the number of elements in the event we're talking about. Okay, and heads is one, there's one head, over the number of elements in the sample space. Notice the notation from our set theory chapter, right? The cardinality of those sets, or the number of elements in each set. Okay, so you just count. All this is saying, now this is important, equally likely outcomes. We want to keep making sure we think about that. So all you do to calculate a probability is calculate the number of elements in your event, which is what you're interested in, and then put it over the number of elements in the sample space, the number of every possible outcome. So for example, if we let S, our sample space, right, be the numbers 1 through 25, and a number is chosen at random, that is with the same chance of being drawn as all the other numbers, in other words, they're equally likely, calculate each of the following probabilities. Okay, so the first one is the event A, that an even number is drawn. So we got to figure out, well, how many numbers are in that set A? They've listed all the even numbers here, and we can see that there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? So the number of elements in set A, your event, is 12. There's 25 numbers in the sample space, so you simply write 12 over 25. That's it. That's all there is to calculating a probability. All right. So keeping that in mind, what if the event B is that there's a number less than 10 and greater than 20 is drawn? Be very careful of our English, right? Pay attention to words like whether it had an and versus an or, because this says and means happens at the same time, remember? So are there any numbers that can be less than 10 and are also greater than 20? No, no such number exists. So there's none like that, 0 over 25. By the way, the denominator is going to be 25 on every single question asked about the set of numbers 1 through 25, right? However, what if it had been an or here? Or means, oh, you're going to draw a number that's either less than 10 or greater than 20. So then think about less than. That's just the numbers 1 through 9, right? It doesn't say less than or equal 10. And or greater than 20, so that's 21 through 25. So 9 plus 5, this one would be, there's 14 possibilities out of our 25 total outcomes had it used or. So be careful about the use of these two words. What if event C is that a number less than 26 is drawn? Okay, well, keep in mind our numbers only go from 1 to 25, so all 25 of them are less than 26, or 1. Right? We're about to talk about these two probabilities, right? A 0% chance that something can happen, 100% chance that something can happen. Or will happen, I guess, not can. If it's 100% chance, it will happen. Okay, another event. The event D, that a prime number is drawn. So first of all, again, I got to see, well, how many of those numbers are prime? And they've graciously listed those here for us, and I just count how many there are. There's 9 that are prime. So again, 9 out of a total possible 25. What about the event E, that a number both even, there's that word and again, and prime? So here's all the primes. Because it said and, it's got to be one of these, and it has to be even. The only one that's even and prime is 2. So there's only one way that that event could happen out of 25 possibilities. Okay, here's our 0 and 1 probability again. Impossible event is an event with no outcomes. it has the probability of 0. A certain event is an event with a probability of 1. And I know we just looked at 2 examples of this, but sometimes people are like, well, how can the probability be 0 or 1? Well, let's think about rolling that die. It's a 6-sided die. What's the probability you roll a 10 on a single 6-sided die? 0, not going to happen. What's the probability you roll a number less than 10? 100%. It will happen because every number on there is less than 10, no matter what you get. So notice if we think about those in terms of percentages, it might help, with that understanding. But probabilities are numbers in between 0 and 1. We can write them as a decimal, a fraction, or a percent. Okay? The vast majority of the time, they're either a decimal or a fraction. But think about this. A 1 converted to a percent is 100%, and a 0 is a 0%. So every now and then we use probabilities as percentages. You hear that on the news when they're talking about the chance of rain. They'll give that as a percentage. But that's the probability that it's going to rain. Right? Okay, so this is a clue. All my probabilities have to be between 0 and 1. So if you get a number to your, an answer to your questions that's asking about a probability that's not between 0 and 1, you know you've made a mistake. Okay, if we draw a card at random from an ordinary deck of playing cards, what's the probability that the card is an ace? And I always ask, if we were in class, I would ask and make sure that everyone understands, what you have with a deck of cards. And sometimes there are students that aren't sure. So if you're not, let's write this down. So there are 52 cards, and you want to write this down to keep it with you while you're answering the questions. There's 52 cards in a deck. All right, in a deck. There's 4 suits. 4 suits. Okay, we have hearts and diamonds that are red, and spades and clubs that are black. Okay, and there's 13 cards in each suit. Oh, it's a different blue. 13 cards in each suit, which is an ace, which is like a 1, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Jack, queen, king. So you have a jack, a queen, and a king in each suit. So the various things that you could be asked about, right, might be the suits. How many are red? Half of them are red, right? There's 13 hearts, 13 diamonds, 13 spades, 13 clubs, right? And each suit, so there's 4 aces, 4 jacks, 4 kings. So since these are called face cards, right, and there's 3 of them in each suit, there's 12 total face cards. So we need all that information to keep that in mind. All right, so find the probability that the card is an ace. All right, well, the top number is how many aces there are. Well, there's an ace of hearts, an ace of diamonds, an ace of spades. There's 4 aces, total of 52 cards, 4 out of 52. And because these are fractional numbers, it goes without saying, you got to reduce your answer. Your calculators can do that. Remember, we've looked at that. If you've forgotten, you contact me and we'll figure out how your calculator can simplify those for you. Okay, so if we draw a card at random from an ordinary deck of playing cards, what's the probability that the card is an ace or a queen? Okay, so we just said each suit has the ace through king, so there's an ace and a queen in each suit, and there's 4 suits, so that's how we get that there's 4 aces and 4 queens. Notice it says or. If it said an ace and a queen, that's 0. There is not a card that has an ace and a queen on it, but an ace or a queen, there's 8 of them. That could be an ace or a queen. 8 out of 52. Once again, simplifies to 2 out of 13. Okay, mutually exclusive, a term we need to be familiar with. Okay, events A and B are mutually exclusive if they have no elements in common. That should be the AND symbol. So if A and B is the empty set, right? No elements in common. For example, consider one spin of the wheel. Okay, so in this case, our sample space are the numbers 0 through 9, because that's everything that's possible. If event A is 0 through 4 and event B is 5, 7, right? Those can occur at the same time. You can't land on one of these and at the same time land on one of these. So those events are called mutually exclusive. I think a better example of that is like we just talked about the ace and the queen, right? What's the probability you draw an ace and a queen? You can't. There's not one card that has an ace and a queen on it. So that's called mutually exclusive if your events cannot happen at the same time. Okay, and now we've got a little formula for our OR probabilities, right? And notice there's a little symbol for OR works, but the one for AND doesn't. So probability of A or B. Here's our first formula. You might want to write it down. However, when we get to the next one, I'm going to basically replace this one with it. We don't need 2 of these, but some of you, okay, that's fine. But to use this one, you got to realize that your events are mutually exclusive. So what this is saying is, if your events are mutually exclusive, like that problem we just had with drawing an ace or a queen, you just add the 2 probabilities. 4 out of 52 plus 4 out of 52. Okay. Now that's going to be different if your events are not mutually exclusive. So if I have this formula, I got to remember that caveat. So 2 mutually exclusive events whose union is the sample space are complementary events. What a weird way to say that. Okay, complementary events, and here's how we talk about the complement. We could also use the apostrophe. Remember again when we talked about sets, we said that this is basically not A or this is not A. So complementary events, right, are like if you roll a 6, then the complement of that is everything else. Or even numbers and odd numbers are complements. They together make up the entire sample space, but they're complete opposites of each other. Okay, so what they're saying is consider the event A being a 2, 4, of tossing a 2 or a 4 using a standard die, then the complement is everything else, 1, 3, 5, 6. Notice what that means. The probability of your event happening is 2 out of 6. And the probability of the complement happening is 4 out of 6 because they have to add and give 6 out of 6. It has to add to give 1, right? Which I think is what's coming now. Yeah, so here's another formula. Now this formula I do want to add. And if I were you guys, they've got 3 versions of it right here, but here's really our formula. You can write all 3 of them down if you want. Just realize they're all 3 the same formula, just written in different formats. But typically, here's your formula. The probability of not A, of A not happening, is 1 minus the probability that A happens. And sometimes I need this formula because sometimes it's easy to calculate the probability that A will happen, right? And so therefore I could get not A. Now sometimes I don't need it. Sometimes I'll just say what's the probability that I don't roll an even number? Oh, well that's a 1, 3, or a 5, right? So I may not need this formula all the time, but sometimes it's difficult to calculate the probability that something will not happen. And so we have this formula. All right, so there's your formula for your list. Complementary events. Non-mutually exclusive events. So let's let E be the event of spinning an even number. So we're talking about this spinner now. Okay, so our even numbers are 18 to 14. Okay, T be the event of spinning a multiple of 7. Oh, we've got a 7, a 21, a 14. Notice these events are not mutually exclusive. Remember, mutually exclusive means can't happen at the same time. But if I roll a 14, it's an even number and it's a multiple of 7. So not mutually exclusive. That means, now here's this again. Should be an and. That means here's our formula for or. And I'm just going to use this formula every single time. I don't need 2 formulas for or. This will work anytime. The one we just had only works if your events are mutually exclusive. Because notice, if your events are mutually exclusive and you plug in here, it's 0. So really, this is the formula I want on my list. If we're doing or probabilities, I find the probability of the first one plus the probability of the second one. But if I don't take out the number of times that they intersect, I will have counted this 14 2 times. So I got to take one of those away, right? So notice the probability it's even. I just say, oh, there's 3 even numbers out of 8. The probability it's a multiple of 7. There's also 3 multiples of 7 out of 8. But I counted the 14 here, and I counted it again here. So then I have to take away however many numbers overlap or intersect, and there's one number that's in both sets for our final probability of 5/8. All right, so there's the formula for our OR probabilities. So we've got our complement and we've got our OR so far. We're going to have a list of formulas by the time we get done with Chapter 9 that I want accessible, right, handy somewhere. Okay, here's a summary of some probability properties. Okay, so some of these you also might want to put on your notes. Okay, the probability of the empty set is 0. The probability of the sample space, in other words, like we said, if you're rolling a single 6-sided die, what's the probability it's less than 10? Well, everything in the sample space. So that's 1. All your probabilities have to be between 0 and 1. Here's those 2 OR formulas, right? Remember our symbol for OR. For OR versus AND, right? So here's an OR probability, an OR probability. This is the one I want. Here's is an event, then this one is missing a notation. So put this on there. Okay, the probability of not A is 1 minus the probability of A. Okay, a golf bag contains 2 red tees, 4 blue tees, and 5 white tees. What's the probability of the event R, that a tee drawn at random is red? So the probability of R, this is our notation, is my bottom number for all these questions is going to be my sample space. So 4, 5, 6, and 5 is 11. And my top number, I just got to see, well, what am I asking about? Red. There's 2 red ones. What's the probability of the event not R? Okay, so the probability of not R, and you can overscore it or apostrophe. Okay, my denominator is still 11. And I could use my formula on this one, or I could just see how many of them are not red. That's 9. But notice, that's the same thing as saying 1 minus 2 elevenths, right? Which is 11 elevenths minus looks like a t instead of over 11, minus 2 11ths, or 9 11ths. What's the probability of the event that a t drawn at random is either red or blue? Because later, I don't think it's in this section, but we're going to add ands. So I got to be careful about the difference between an or and an and probability. So what's the probability that it's red, or blue? Okay, well, it's simply the probability that it's going to be red, which we've already calculated, plus the probability that it's going to be blue, and because there's 4 blue t's, that's 4 out of 11, minus the probability that it's red and blue. There are no t's that are red and blue on the same t, so that's a 0, right? Or I could have just said, oh, they're mutually exclusive to start with, so I use that first formula if you want to keep up with both of them. So 4 plus 2, they got a common denominator already. Geometric probabilities, or area models. A probability model that uses geometric shapes is an area model. When area models are used to determine probabilities geometrically, outcomes are associated with points chosen at random in a geometric region that represents a sample space. This process is referred to as finding geometric probabilities. So like that very first slide, I think, where I drew, the dartboard and covered a fourth of it black, things like that, or the spinner, they had a question about a spinner, right? So where you're looking at a geometric shape. Design a geometric model for the following experiments. Tossing a fair coin. A fair coin. Don't toss a corn. Toss a fair coin. Okay, so there's no particular reason why it has to look like this. It would have been perfectly fine had they drawn the line like this, or like this. Any way that just divides it up half and half, right? They've gotten a little creative here like this. But what would not represent it is if they had drawn it like that, right? That's not what's represented by the model. Okay, or here rolling a fair die. So they've just made a spinner where your only outcomes, and they all have to be the same size. That's important, equally likely, right? Or 1 through 6. So use the spinner and find the geometric probabilities. The number is a factor of 35. So I want the probability of A. For one thing, I know my denominator is going to be 6, right? Because that's all the possible outcomes. And all I have to do is say, well, how many of them are factors of 35? Don't forget about 1, right? So 1 is a factor of 35. 5 is a factor of 35. Those are the only numbers that divide 35. Don't forget to reduce. Okay, the probability of B. What's our denominator? Yeah, 6. Okay. The number is 1 or even. Oh, 1 or even. I'm going to do the probability that it's 1. There's only one number that's 1. Plus the probability it's even. 1, 2, 3 of them are even, minus the probability that it's 1 and also even, which is none of them, right? So 4, 6, or 2/3. What about C? The number is prime or a multiple of 3. All right, so let's say the number is prime. Okay, remember 1's neither prime nor composite. So there's prime, 1, 2, 3 of them are prime out of 6, or a multiple of 3. So I'm going to count how many of them are multiples of 3. Well, that's 3 and 6. So there's 2 of those. minus the ones that's prime and also a multiple of 3. There's one that's in both categories. I counted that 3 right here, and then I counted it again right here, so I got to take one of those off. So 5 minus 1, well, that has the same probability as our previous question. Okay, what's the probability that the number is 8? Right, nothing is 8. Don't forget to simplify all fractions. And what about E? That the number is less than 8. Every single one of these numbers 1 through 6 is less than 8. Okay, let me know if you have questions. Okay, according to the weather report, there is a 30% chance of rain today. So what's the probability it will not rain today? Oh, so we're trying to find the probability that it's not going to rain, right? So technically I have this formula, but this is another one where, hey, if there's a 30% chance it's going to rain, I know there's a 70% chance it's not going to rain. But there's my using the formula. If A and B are mutually exclusive, all right, so that tells me they cannot happen at the same time. There's no overlap. And the probability of A is 0.2 and the probability of B is 0.5. What is the probability of A or B? Well, I've got a formula. Anytime it asks me about the probability of A or B, I just add them together. And it says they're mutually exclusive. So once again, that's 0. Same as the chance it's not going to rain today. Okay, I think that's the last slide, but let me double check for us. Oh, no, it's not the last slide. Okay, glad I checked. This is a good one. A box contains 5 white balls, 3 black balls, and 2 red balls. If only red balls are added to the box, how many must be added so that the probability of the event of drawing a red ball is 3/4? Okay, so I want this thing to equal 3/4, right? I want my probability to be 3/4. And I'm talking about the probability of drawing a red ball. So let me just put up the probability right now of drawing a red ball. Well, there's 2 red balls out of 5, 8, 10 total balls. It's not 3/4. I want to add enough red balls to make this 3/4. So if I add red balls, it's going to add balls to the total number of balls in there, but it's also going to add to the red balls because here's my number of red balls. There's my proportion. We can solve it by cross multiplying, whatever method you want. Get rid of the fraction, cross multiply. I'm going to cross multiply on this one. So I would have 4 times 10 plus x equals 3 times 2 plus x, or 40 plus 4x equals 6 plus 3x, right? Getting rid of the parentheses. Let's subtract 3x from both sides. And subtract 40. I can't have that, so let me see where I made a mistake. Because I can't have my probability or my x, this isn't the probability, or my x equaling negative balls. I'm adding balls to it. So let me see what I did. Only red balls are added to the box. Okay, we've got 10 balls. We're drawing a red ball to be 3/4. Okay, so that's, look what I did. I didn't really cross multiply. All right, let's change up this. All right. All right, so if I'm cross multiplying, right, we have 3 times 10 plus x and 4 times 2 plus x. Okay, so here we have 30 plus 3x equals 8 plus 4x. Now if I subtract 3 x's from both sides, my x is over here, and then I'm going to subtract 8 from both sides. Okay, so this is how many red balls we would need to add to the box. Notice I can double check this. If I added 22 red balls, that means I now have 24 red balls total. So if I do my probability, there's 26 out of 24 plus 5 is 29 out of 32. Why am I getting crazy here? Oh, because, oh, wow. Sorry, guys. Okay, so if we're checking, we have to know how we're checking, right? Okay, that means there's 24 red balls, but, and I don't know why I put 26 up there for one thing. Let me erase that too. All right, 24 total red balls. Right, if I put 22 red balls in there, then I've got 24 total red balls. And I had 10 balls, so if I put 22 balls in there with the 10, that's 32. And now both of those will simplify by dividing an 8 out of there. All right. Woo! Confused myself on that one. I hope you guys are okay with it. Okay. All right, what about the next one? If only black balls are added to the original box, and so that tells me to go back up here. We're not talking about adding to this one with the 24 red balls now. So if only black balls are added to the original box, how many balls must be added so that the probability of drawing a white ball is 1/4? All right, notice this one talked about adding red balls and having your probability of drawing a red ball. This one is talking about adding black balls, but the probability is about drawing a white ball. So be careful of that. All right, so I'm doing my probability of drawing a white ball. There are 5 white balls out of a total of 10 total balls. And I can see, whoops, no, that's not the same probability. So I'm going to add black balls to the box. I'm going to add balls to the total thing, but it's not going to change up here because this is the number of white balls. So that number this time isn't going to change accordingly like it did up here because both of these were involving red balls, right? All right, and then again, cross multiply. Let's cross this time. So 5 times 4 is 1 times 10 plus x, or 20 is 10 plus x. Subtract 10 from both sides. So I would need to add 10 black balls. Okay, which would give me 5/20, 1/4. Okay, I think this is the last slide. Let me double check. Okay, it was. So there's 9-1, guys. Let me know if you have any questions. All right, bye-bye.